Today our lesson is going to be on analyzing graphs. Make sure that you have the learning target written down at the top of your notes. I gave you a spot to write that. So learning target, make sure you fill that in. I can write algebraic expressions by analyzing graphs. All right, the next thing, translate a graph into an expression. To do that, here are the steps. The first thing you need to do is write the ordered pairs in a table. So some of the graphs that they give us, they're going to actually write the ordered pairs beside the point. Some of them you will have to look at the point and decide what the ordered pair is and then record it in a table. The second step is to analyze the table. So this is the first one, here's the second one. Analyze the table. What is the common difference? Okay, just like what we've been doing in the days before this week, we've been looking at the table and saying, how is this changing? We take that number, put it in front of n, so that number times n. Then we're going to check it. So that's this third step right here. Remember, sometimes you'll need to add or subtract a number to complete the pattern. So when we check it with one of those values on the top, if it is that number that's in the table, that's what we get, then we're just going to say, plus 0. So we don't need to add or subtract anything. If it was something that's a little bit different, like say we get out 4 when we multiply, but in the table it says 5. Well, to get from 4 to 5, I know I need to add 1. So it's the exact same thing that we've been doing. The only difference is now they're not going to give you the table. They're going to give you a graph, and you've got to put those points, those ordered pairs, into a table and then use that. All right, so we've got this example on page 288. It says an electric train set runs on a track that is 25 meters long. The graph shows how many times the electric train goes around its track each minute. Part A says write an algebraic expression to represent the data in the graph. So we need to record these ordered pairs. Okay, we want to do them in order. So the first one is 1 and 2.5. The second point is going to be 2 and 5. The third point, 3 and 7.5. The fourth point, 4, 10. The fifth point, 5 and 12.5. The sixth point is 6 and 15. And the seventh point is 7 and 17.5. So now I've completed this table. Now we just need to analyze it. So looking through here, I want to know how is it changing as I go in order of the sequence. What's happening every time? So I can clearly see right here, especially from 5 to 7.5, that it's going up 2.5. Okay, so for my expression, I'm going to start off as 2.5n. All right, now remember we've got to check that, so you can choose any of these values. I am going to choose, let's see, I'm going to choose 2. So if I do 2.5 times 2, 2.5 times 2 gives me 5. Well, looking back at my table, that's what I wanted out, so I don't have to add or subtract anything. So my expression is just 2.5n. Part B says, use the expression to find how many times a train would circle the track in 1 hour. All right, now we've got to go back and think. In this graph, they're talking about time in minutes. Right here, time in minutes. So if they say 1 hour, how many minutes are in 1 hour? Well, there are 60 minutes in 1 hour. So going back to my expression, I want to start with 2.5. Instead of n, I want to fill in 60 because that's how many minutes are in 1 hour. When we multiply that, 2.5 times 60 actually gives us 150. So the train is going to circle the track 150 times in 1 hour. All right, let's look at the next one. Exact same thing, except this time our situation says the graph shows Bruce's distance from home on a car trip. Okay, so we've got some ordered pairs here. Our smallest x value is what we want to start with. That's going to be 0. And that 0, we're at 350. The next one would be 1. So 1 and 280. The next one's going to be 2 and 210. The third one is 3 and 140. The fourth one is 4 and 70, fourth term. And then my fifth one is 5 and 0. Now, we know that these are arithmetic sequences, so they're changing the same every single time. So if one of these looks easier for you to figure out how it's changing, then go ahead and look at that. So my eyes are instantly drawn to this end. Between 4 and 5, I can very easily see that we're subtracting 70. Now, from 0 to 1, I may not be able to tell that as easily, from 350 to 280. However, it is still going down negative 70. So negative 70 in. All right, we've got to check it though. All right, so any time that you see 0, I would definitely use that one. That makes it just a little bit easier. So when I do negative 70 times 0, I get 0. But I need 350. So to go from 0 to 350, we have to add 350. So coming back to my expression, I've got to add that 350. So my expression is going to be negative 70n plus 350. The D part of this tells us that we want to use the expression to find Bruce's distance from home after driving 2.5 hours. Now if we look, our time is in hours, so we actually want to fill that in. So we want to do negative 70 times 2.5 plus 350. All right, so multiplying that, we're going to get negative 175 plus 350, which is going to give us positive 175. So using this expression, his distance from home is going to be 175 miles. So if we look over here on our graph, it tells us that his distance is in miles. All right, these are going to be fill in the blank. So linear graphs. The graphs of the relations in the previous examples are considered linear because the points fall in a straight line. So if we go back and we look at these, they are linear, okay? If you look, those points right there are in a straight line, okay? And then if you look on this one as well, those points fall in a straight line. If it's arithmetic, it is going to be linear. All right, so they fall in a straight line. If the data in a linear graph falls on a line that slants up from left to right, so what I mean is it looks like it's climbing or increasing, it's going up, then the coefficient of the variable is going to be positive. An example of that would be something like 2x. Okay, so if it's going up, it's going to have a positive coefficient. Okay, so if we go back and look at our expressions, right here, this line is, these points are going up from left to right, and notice that we've got a positive 2.5 there. Okay, so in front of our n, or in front of our variable, we've got a positive coefficient. That tells me that that line is going to be positive. It's going to be increasing. All right, the last one, if the data in a linear graph falls on a line that slants down, so that means it's going to be falling from left to right, then the coefficient of the variable is going to be negative. So example, that would be like negative 2x. If we go back and look here at this last example, you can see that those points are falling. And if you look in front of the variable, it is a negative 70, as it should be because that line is going down or decreasing. So the coefficient is negative. I know my points are going to go down. So that's kind of a way you can check. When you get that expression, if your points are increasing, if they're going up from left to right, you should have a positive number in front of n. If your points are going down, like Bruce's distance from home, then you should have a negative number in front of n. So again, if it's going to slant up, if the expression has a positive coefficient, it's going to slant down if the expression has a negative coefficient. Now you need to log on to Canvas, flip this paper over, and on Canvas you can find the Skills Practice Worksheet. I've already drawn tables there for you. You just need to fill them in from the graphs and then find the expression for each one of those.